Welcome to Frank Staiano Explains and to the Algorithms course at the University of Cambridge. Like the various flavors of search trees we have explained in the previous 4 videos, the hash tables are another data structure that implements the dictionary abstract data type. The hash table doesn't require an order to be defined on the keys, because all the hash table does is a straightforward lookup. You give the hash table a key, you get back a value. None of this predecessor, successor, minimum and maximum extra stuff that you get with the search trees. On the plus side, instead of getting the answer in big O of log n, which wasn't bad, you get it in amortized constant cost, which you must agree is pretty amazing. So let's hit the like button and have a look at how it's done. We've seen a variety of trees and of techniques for keeping these search trees balanced, all ultimately derived from the B-tree ideas. But there's another way to implement the table data structure, or dictionary data structure, which is what you use when you don't actually care about successor, predecessor, minimum, and maximum. You just care about retrieving the key and its satellite data based on the value of the key, regardless of what other keys might do. And so in that case, you don't even attempt to preserve an order. You just dump things in your data structure, each of them independently of the others. And it's obvious to see that the array would be a neat way of doing that, provided that you could fit things in your array. So this is U is the universe of your keys, which look like integers, and then you have an array that's indexed by these integers, and if you want to stick a particular key, for example 2, in your table, you just put it in position 2 of your array, and if you wanted to stick key 5 in your array, you stick it in position 5 of your array. And here, in fact, the array is an array of pointers to records which have a key and the satellite data, which is what you actually want to retrieve from the key. You could imagine having an array of records instead of an array of pointers to records, but you have to make sure that you have a way of distinguishing a record where nothing has been stored from a record that has not been initialized. So having these pointers lets you keep this distinction. The trouble with this setting is that many times the thing you want to use as a key for indexing your values comes from a very large universe. And here, your array has to have indices that cover the whole universe. So if the universe is the integers from 0 to 9, then you are doing fine building an array. But if the space of your keys is, for example, the surnames of your students, well, how many students? Of the order of 10,000. If you're in a much larger university, of the order of 100,000. But the surnames, I mean, how long is a surname? Let's say that the surname is 10 letters. Well, there already exist people with much longer surnames than 10 letters, but 10 bytes would be 80 bits. So you would have 2 to the 80, which is a much bigger number than 100,000. So 2 to the 80, how big is 2 to the 80? 2 to the 10 is 1,000. 2 to the 20 is 1,000,000. 2 to the 30 is 1,000,000,000. 2 to the 40 is 1,000,000,000,000. 2 to the 80 is some kind of octillion or whatever. It's more RAM than you can buy. It's more disk than you can buy. It's a monstrously large size for an array that is only supposed to hold 100,000. So nobody in their right mind would ever want to have an array that's indexed by the key in a situation where the key universe is large, because usually you're only using a very tiny fraction of this universe. So what you want to do is to map your relatively small used part of the key space onto an array. And then the array still makes sense. You're not wasting the vast majority of your array for empty space. And this is a picture of a strategy where I use some magic function h to map between the universe of keys and the indices of my array. So h takes a value from the universe of keys, which could be very large, and produces an integer in a range 0 to m, which is the size of my array. And I dimension this array not thinking of the size of the universe of keys, but thinking of how many keys I expect to store in there with a bit of margin. So this will be closer to the 100,000 students I'm expecting to put in than to the 2 to the 80 or 2 to the 160, however many possible keys I might have if I consider all possible strings of that length, most of which I'll never use. So clearly I'll want to have some margin. It's obvious that this hash function, just from a counting argument, a cardinality argument, there will exist some values of k that produce the same hash output, because there are many more values in the universe of keys than there are slots from 0 to m minus 1. So this is an example where, unfortunately, two of the keys I actually use, k2 and k5, hash to the same value, and therefore they would end up pointing at the same slot in this table. So it is not as easy as it was in this picture, where I could just take my key value pair and slot it in the slot that's pointed to by the key, in this case indirectly through the hash function, because sometimes two different ones will map to the same slot. So I'll need to have some strategy for dealing with the case in which two distinct keys hash to the same slot. And the easiest way to resolve these collisions is just to have a linked list at this point instead of just a value. Here I had a pointer to a record, and here I could have a pointer to the first record in a linked list. And then this linked list would contain all the keys that hashed to the same value. But still, I'm hoping to build a hash function that does a good job of spreading the keys uniformly across this range from 0 to m minus 1. And so I expect that if I have dimensioned this table to be a bit larger than the number of keys that I want to put in, then it will be an infrequent occurrence for me to have a chain that is longer than one element. But it may still happen, and so I have to cater for that case. So here is a picture of having done just that, where these keys K2 and K5 and even K7 all of them map to this slot. And this slot is a pointer to a linked list, in fact a doubly linked list of records which contain the K5, K2 and K7. So in the graphical notation that I've used in other slides, these are pointers, and so start as a circle. These ones are also pointers. And this is what I've indicated with the ground symbol, the null pointer, over here. The reason for wanting to use a doubly linked list as opposed to a singly linked list, which is what we've used in most other occasions so far, is so that when I need to delete an item, and remember that the interface I gave you for the deletion from a table somewhere a few pages earlier said that you'd actually give a pointer to the node as opposed to the value of the key, so as to separate the operation of searching for the item from that of deleting the item, and also so as to cater for the case in which I allowed duplicates, and so I would have no ambiguity about which item I actually wanted to delete. Now we're in a situation where we don't allow duplicates. In a hash table, it would make no sense to have duplicates. But still, if I assume that I am giving you the pointer of the item I want to delete, for example, this one, then if I had a singly linked list, I would have to change the pointer of the item pointed to this one, so that it no longer pointed to this one, but pointed to what's appropriate, which is the next item after this one, in this case empty. In another case, there could be some other item following here, and this would have to be patched in by changing this pointer. Now, if I only had the forward pointers, if I say, please delete this, I would have to start again from hashing this K7, finding that it goes to this slot, and then following this through until I found someone whose next pointer, good morning, was K7, the node with K7. So then I would get to here after having linearly traversed this one. In order to save this pain, then if I have a doubly linked list, this one will tell me who its predecessor is, and that's the one whose next pointer I have to change to point to this one. So the doubly linked list is a useful thing to have in order to facilitate deletions from the table. If my hash table is properly dimensioned, then I would expect, properly dimensioned means a sufficiently greater number of slots than number of keys that I put in. I would expect the average length of these not to exceed 1. This is actually called the loading factor of the table. Loading factor is indicated with the letter alpha. And this alpha indicates how many keys there are in the table divided how many slots there are in the table. And so if you make this alpha less than 1, then you expect these, obviously on average, these linked lists are going to be of length at most 1. Some of them will be empty, but there will still be some cases where there are some collisions and length is greater than 1. In an arrangement like this, it is actually conceivable to allow the number of items in the table to grow beyond an alpha of 1. You can still keep adding things, but the more you do so, the more you will have collisions, and the more you will have linked lists of some length greater than 1. But it is something that still works. It just gives poorer performance. There's another arrangement, however, which tries to save on the space that I have to waste on all these pointers. And I say, well, this space of the pointers, I could put it to better use just by storing more keys. And if I do that, I will, because I'm using my memory for more of the things that matter, I will be able to fill in a greater n before I get to a filled up state. And with hash tables, as I said, we might want to try the alternative strategy of not making little chains, but to store everything in the table, which, because we saved the space that we were devoting to the pointers, we can afford to make bigger. So all the possible keys are stored in the table. And what happens when we have a collision? When we have a collision, it's still the same pictures as before, isn't it? Yeah. Okay, so they're useless. Right. When we have a collision, in the case, I might just make myself my own table then. When we have a collision, it means that two keys of different values will point to the same slot. So, for example, H5 and H7 both point to this slot. Then the first one who gets there on insertion will be stored. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I said h of k5 equals 6. Then I store k5 in here. Then I said there's a collision, and so h of k7 is also equal to 6. Then I need to store k6, k7 somewhere, and it says you should store it here, but I can't because it's already with k5. So I should put it somewhere else. Okay, well, there's plenty more places where I could put it, but the problem is finding it again later. So what should I do? I could put it just in the next free slot, like here. K7 it was. So then I want to put in some other key, hash of K15, and it hashes to 3. Then I look for 3, 3 looks empty, okay, so then I put K15 in here. Great. Then I hash K74, and it hashes to value 5. That's empty, great, okay, so K74 goes there. Now, unfortunately, I hit K1, which also hashes to 5. Then I try putting it in 5, but it's already taken. Then I try the next one. But it's also already taken. Try the next one. It's also already taken. So K1 ends up over here. So I kind of have a chain like I used to have in the previous case, but the chain is now spread among the empty slot of this table. There's some trouble here, which I'm sure you notice, which is that the lists are not independent of each other because they all spread over whatever the empty slots were of this table, and the empty slots are all common. And so these lists kind of step on each other. How would I ever retrieve anything from a table like this? So if I look something up, if I say, well, where is the key value pair for example, K5? And I first hash K5, and it gives me 6. Good morning. And K5 is found here. Great. Then I get K5 and its value. But what if I want to look for K1? Then K1 hashes to 5, and I look for here, and this is K74. It's not K1. I was looking for K1. This must be a mistake. So maybe K1 was stored in the one after that because it was occupied. But this is actually K5. It's still not K1. So let me try the next one. It's K7. Oh, it's not K1. K1. Finally, I found it after traveling this. So Logically, it's not so bad. I can just follow the same procedure when I search. But it is a bit of a nuisance, because these things, if I use my colors, then this K5 and K7 both hashed to 6. So this is one kind of chain between K5 and K7. And K1 and K74 hashed to 5, but K1 had to go like this. These two chains overlap. So even though there were only two things that conflicted on the same value, on the same index 5, actually the chain for this K1 was 4 long, because it also had to skip over the things that conflicted on index 6 that were also taking up space. So this chain has to step over the things of another chain, which is completely unrelated. And so compared to the situation where I was making individual chains, the individual chain for this one would have been too long, but actually here I have to walk 4. And so this is somewhat undesirable. Clearly, everything that hashes to the same value will end up in the same chain, and I will have to follow that. But this fact that I have to step over other things because there was an accumulation of junk over here is a bit unhappy. So this is the probing function of where I look for things in the table. Oops. Expressed as a hash which takes not only the key as a parameter, but also the number of the probe. So the first time is time 0, the next time is time 1, the next time is time 2. And so the real hash function is this h prime, and I use that plus the probe number as an offset to decide where to go. This is successive attempts in case the place that I wanted was already taken. And notice another annoyance with this, which is what happens in the case of deletion. What happens in the case of deletion? If I were to delete key 7, from the table, can you see trouble? There's trouble because how do when I search for a key, so far I've only just showed what happens when the key is in the table because I put it in earlier. What if I search for what if I search for key 2? I've never used key 2. So I look for h of K2, and h of K2 happens to be 1. And then I look in here, and position 1 is empty, and therefore I say not found. Okay, K2 is not found in my table because the slot was empty. But now what happens if I say, now look for K1. So K2 not found. Because the slot in position 1 was empty. Now if I look for K1, K1 hashes to 5. So I look in position 5, and it's occupied by something that's not K1, so I have to go look for the next one. This one is K5, still not K1, so I have to look for the next one. Next one is empty. So I'm basically in the situation here. I look for the place where K1 would have been, and I found that it's empty. Therefore, I should say it's not in the table. Well, it's not true. It is in the table, except I deleted the thing that I would have had to skip over if I hadn't deleted it. And so I miss getting to the place where K1 was. So what I need to do in this case is not to delete it by saying this slot is now empty, but delete it by saying this slot is now deleted. And deleted is different from empty. In the sense that when I look for a key in the table, I treat the deleted entries as the same as if they contained a key that's not the one that I was seeking. However, when I insert, I treat the deleted entries as empty slots. I can overwrite this thing, but I cannot stop my search at this thing. So this type of probing function is unsatisfactory. And so people have come up with ingenious alternatives for making a probing function that spread things around a little better. For example, this strategy here, called quadratic probing, makes a probing function that on successive probes does not just have a linear function of the originally pointed value plus the probe number, but a quadratic function. And this quadratic function means that your jumps start spreading out. And so if you start from different places, you don't percolate through the same region, because sometimes you will start jumping around with bigger steps. If you started from earlier on, then by the time you're here, your quadratic steps will be larger. Of course, all of these things are modulo m. I haven't shown wrapping around, but all these things wrap around at the beginning, otherwise you'd never use all the slots. This is something that gives much better performance than this probe sequence here of linear probing, but it still has the trouble that two values like, in our case, K5 and K7, because they hash, both of them hash the same thing, they would have this base in common, and the offset depends on the number of probes that I'm doing. So it's going to be the same sequence for both of them. So these things will keep colliding on all the places that they probe. If they hash to the same slot originally, then their two sequences are the same. And so I cannot avoid collision there. To fix that problem, there is yet another strategy, which is called double hashing. And in this one, I use two hash functions, one to give me the base and one to give me the step of the offset. The price I pay for this is computing two separate hash functions per probe, but the advantage I get in return is that two things that hashed to the same base might still have different steps in their offset, and so their sequences are different. So, as far as these probing sequences are concerned, when you are designing your own probing sequence, you must also make sure, it's not easy just throwing parameters at these things. You must make sure that the probe sequences you construct use up all the entries in the table. And it is interesting to try things out with a program to see if the things you do end up creating a permutation of 0 to m minus 1 or not, instead causing just concentrations of values in certain slots only. And it's not as trivial as it sounds to find parameters that will actually spread across the whole range of indices in the table for every value you put in. I want to say a couple of words about last time's technical topic, which was the hash tables. So we've seen two styles. I've had a lot of supervisions yesterday, so I'm aware of some things that didn't quite get across. We've seen two styles of hash tables which work differently. One of them is called the chaining method, and you don't store your items in the hash table itself. You store them in little chains that hang off the hash table. And there's another style called open addressing, which works differently. And you store everything inside the hash table itself, You don't have anything outside the hash table, therefore you save the space of pointers. Chaining is the one with little chains. Open addressing is the one where the address of an item is not uniquely determined by its hash, because it may go somewhere else if that place was already full. Please do not confuse the two. Please do not be confused by other people using other names for these. I will not say the names so as not to confuse you, but they are in your handout. Don't use these other names. Use consistently these names, which are the same ones as your textbook, but be aware of the difference. And the couple of things I wanted to say that I noticed I didn't say last time are that unlike the chaining case, the open addressing case may run out of space. I did say that because the table is closed and you can only put things in slots that exist in the table. So what happens when the table gets full? What happens when the table gets full? You can either give up, but that's not a very nice thing to do if a piece of your library gives up on you. And you can instead say, okay, I will, under the carpet, without telling anyone, I will make a bigger table. And I will transfer everything from the old table to the new table. And then I will start using the new table. And that's when your computer has a kind of hiccup. You're doing something, and it keeps doing it. That's because it was doing something like that. And this, this trick looks like a very bad thing to do, because then just one access for inserting one item costs you all the cost of making a table that's twice as big and copying everything from the old one to the new one and so on. But if I had already taught you amortized analysis, which I haven't because it's now done in the second part of the course, then we would be able to analyze this cost and see that if we spread it out over all the operations you do, it's not so bad. In fact, it's actually rather good, because with amortized analysis, you can say the cost of inserting into this open addressing table, even if it expands when needed, if it expands by a factor of 2 every time it needs to, will still be constant. So access time to a hash table is constant, even if you use this trick. And even in the case of the chaining one, you will get constant time, provided you keep a reasonable loading factor. So here the loading factor could exceed 1, but here it has to be under 1, and it had better not be too close to 1, otherwise you will have very slow performance, because you will be following many chains internally that may overlap with each other. In the library function for implementing the hash table that's provided with Java, the load factor that triggers a doubling of the size is 0.75. So when you are 3/4 full, it makes one that's twice as big. And it works very well. So thing to remember is the amortized cost of accessing a hash table is constant.